Welcome to the STEM Pathways podcast, where we delve into the fascinating world of science, technology, engineering, and math. I'm your host, Rohan Sharma, a passionate explorer of all things STEM. Each episode, we bring you captivating stories, cutting edge research, and inspiring interviews with experts and enthusiasts who are pushing the boundaries of innovation. Whether you're a student, a professional, or just curious about how the world works, join us as we unlock the mysteries of the universe and explore the endless possibilities of STEM. Let's get started. Today, I'll be interviewing Dan Garcia, who holds a bachelor's from MIT and a master's and PhD from UC Berkeley, where he is currently a professor. How are you doing today?
I'm doing great. Thank you for the invitation to be on this podcast.
Yeah, thank you for joining me. So to start off, I wanted to ask, what made you major in computer science in college?
Well, in high school, I took a computer science class and fell in love. Absolutely fell in love. I was already a pretty strong math student, and they had my pre-calculus class. I guess it was my junior year. Half of the year was pre-calculus. I guess we only needed half a year, and the other half was let's learn some basic programming. My teacher, Mr. White, had gotten a grant, I guess, to have some Radio Shack TRS 80 computers, and we learned basic programming, and I just fell to it. Everything felt so logical. He was a great teacher, first of all, and I just loved the material. I couldn't get enough of it. And I said, how do I do that? How do we do more of this? And so when I was applying to college, I applied to MIT, and I couldn't decide whether I wanted to major in physics, which I loved, or calculus or math, which I loved, or computer science. And after the first year, it was clear that computer science was the one for me.
Yeah. So what was your experience like while getting your bachelor's?
Well, it's I went to a small high school, a very small high school, about 100 kids, Cooperstown, Central School, upstate New York, and I was the math and CS guy out of 100 kids. It was a small school, and when I got to MIT, I'm now part of 1,000, and many of those kids have been programming for years and years. They own computers. I didn't own a computer, so in some sense, out of my league. They were much better than I was in that first class. I worked hard to try to catch up and try to be there. And by the end, I think I did fairly well. So I did well enough at least to impress Berkeley and let them admit me to graduate school. So it really took me a while to get used to the rhythm and pace of college, as it takes a lot of kids. I was maybe a little immature. I was only 17 years old. I turned 18 like in February, so I was very young. And immature and didn't have good study habits. I was kind of an athlete, so I joined about 7 or 8 different intramural sports, played a ton of sports. And so that stretched me pretty thin in terms of my time I had for school. So if I were to go back in time and tell my younger self, I would say, don't do as many sports, maybe spend a little bit more time in the books. But I really enjoyed my time. The nice thing about MIT is the first year is pass fail, and I didn't fail any classes. I did fairly well. But if the first year had been grades, I think I might have treated it. I felt that was a little buffer there, that if I got a B, it was okay in some of my classes. But eventually, got on the right track and did very well, and started to move from sitting in the back of the classroom to sitting in the front of the classroom. That was interesting, where I started to kind of own my own education. I tell my own young students that I'm going to have class starts next week. I'm going to tell them the best practice to be in my class and do well is to go to office. I never went to any office hours. Go to all the office hours, get to know the professors. I didn't get to know many professors. I did do some research, and that was exciting. And sit in the front. Lose that feeling of fear that you don't want them to call on you. Just make sure you feel like you own your education. So it's a perspective difference. And the moment I did that, I've been doing that ever since. Now, literally since junior year of college, I spent 5 years at MIT getting 2 degrees in CS and EE. Since then, like literally 10, 9.5 years of grad school, 3 years of undergrad, I was sitting in the front, owning it, and really, really enjoying it. I've done it ever since. Got a conference as I sit in the front row. So it's great to feel. And it's funny, my colleagues don't. My colleagues go in and sit in the back and are quiet on their laptop. And I'm like, no, why aren't you sitting in the front row? Like, why aren't you doing what we tell our students to do? So it's kind of a funny thing. So yeah, it took me a while to get used to it. Fell in love with computer graphics, got to graduate school, fell in love with teaching, and applied as a teaching professor, and I got that. So every kind of step, I fell in love with something that got me to the next level. Fell in love with CS, get into MIT. Fell in love with graphics, get into Berkeley. Fell in love with teaching, get a position. So it's kind of funny how each of these was like something was new and amazing, and that led me to the next level. It's great.
Yeah. Further on that, did you already know you wanted to go into academia while you were doing your bachelor's, or is that in grad school?
No. I just didn't want to work. Everybody, every single person I knew at MIT was going to work for Oracle or Microsoft, and it didn't seem that when I'd heard the stories of what they were doing wasn't exciting to me. And I loved school. I wanted to do more of it. So I knew I wanted to go to graduate school. And a funny story, I went to the West Coast for a Grateful Dead show. You might not have heard of the Grateful Dead, but they're an old band and they were amazing. I went to see the Grateful Dead play in Oakland Coliseum. It's called the New Year's show. And we stayed up all night to bring the New Year's in, listen to music. It was amazing. And the weather was amazing. Here I am in California, and you're from Wisconsin. I was from Boston, so I left 6 or 10 inches of snow. I arrive in California, and I get off the plane, and it's 70 degrees, and I'm in shorts, and I'm like, wait, I didn't expect it to be that warm. It was gorgeous. So something about California weather, the people, the music, the culture, the politics, all of those kind of warmed up in me. I said, I need to apply to something out here. And then there was a really transformational session that one of the professors gave. So two professors, they locked the door and they said, this is a secret room where we're going to rank, you yell out of college and we'll tell you what we think of that college. So people, yelled out, blah, 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 blah. And when they got to Berkeley, and by the way, they put number of stars behind each college. So 4 stars was the max. When they got to Berkeley, they put 5 stars. I was like, whoa, that's pretty cool. And they got to MIT and they put 5 stars. I was like, well, I can either go to MIT or Berkeley. So I wanted to shoot for the best. So I applied to both, got into Berkeley, and the rest is history. So that was my story of how I got here. It's kind of funny.
Yeah. So what was your experience like while getting your master's?
Well, really, I was getting a PhD. I got in for the PhD program. Master's was kind of an afterthought. Master's was something I did on the way. And I came in with this, and this is the connection to maybe this is a nice pivot and segue to this talk. I came in with a love of game theory. I had some summer jobs where I learned to program tic-tac-toe. So just like Bill Gates, when he said, the first program was programming tic-tac-toe, my first program for me, that wasn't a program for, a course, something that somebody had told me to do, was to try to solve tic-tac-toe and understand how to put not just an AI, but to actually solve it, to be able to look at every single possible move path in the game tree, and then use that to bubble its way up so that I would know whether it's good or bad to do something. So I did that and I fell in love. I was like, that's pretty cool. My system plays perfectly. So I kept adding to it and adding to it and adding to it. Then I added more games and I added graphics. It was a super fun thing. And then I got to Berkeley and there's this amazing professor named Elwin Berlekamp, who was one of the 3, almost like the Holy Trinity. These 3, Conway, Guy, and Berlekamp, the 3 people had written a book called Winning Ways, 1 and 2, a red and blue book. And I had taken a class in game theory, so I knew about them. I had the book, and I wait, Berlekamp's at Berkeley? Oh my god, I didn't even realize. So I went over and I said, do you mind if I work with you for a master's? He said, that sounds fun. So I got a master's with Professor Berlekamp in game theory, and that led to the master's. So on my way to the PhD, I stopped off. It's like they stop on the side of the road. I stopped on the side of the road for the master's in game theory, then went back to do a computer graphics PhD. So that might segue into me sharing some slides about this research project that I've continued. When I got to Berkeley, I decided, let me not let die this interest in game theory. Let me see if I can revive that. My master's project, can I revive it and add more games and have students add more games and have students understand what I understood about the principles of computational, using a computer for game theory purposes, computational game theory. Can we do that? The field that Berlekamp was doing is combinatorial game theory, kind of the mathematics of surreal numbers and games at a normal form where the last person to move wins. I wanted to focus on the general forms of game theory. By the way, no games that I consider have any chance. So this is important. It's only the games that have no chance and are perfect information. So I could, like tic-tac-toe and Connect 4 and chess and Go and all that. So could I create software? Could I build on the software that I already built for my master's in a student project? And that's exactly what I'm going to talk about now in my research.
Yeah. So do you want to share your screen? You mean just get
Sure.
right in?
Yeah. Thank you. All right. I'm excited. Okay. So this is the slide deck that I have. Hope you can see it. This is the logo that Cassie Guy, an amazing graphic artist who worked with me years and years ago, designed. It's Games Crafters. This is the O and X, which is like our symbol of think it looks like the singular logo, but we did this, I think, in parallel to that. It's not like we stole that idea. But this is Games Crafters. You can see the word Games Crafters. And the idea behind this was it's like Lens Crafters. If you remember that, Lens Crafters had this logo, lenses in under an hour. And so this was the idea that if you really got good at doing Games Crafters, you could go from nothing to a working game in under an hour. That was pretty cool. So it was Games Crafters, games in under an hour. And we have a website. I encourage everybody to visit this, gamescrafters.berkeley.edu. Hope you can see my screen and my cursor. And so this is a talk on my Games Crafters project. So when people ask me, if you say, hey, I attended this talk by Dan Garcia on game theory, they might ask you, what kind of game theory? Because there actually are 3 different kinds of game theory. And for the most part, if you just said game theory, they mean economic game theory. And this is, it traces back to von Neumann and Morgenstern's theory of games and economic behavior. It's matrix games. If you've heard of the prisoner's dilemma, it's about that. It's heralded by incomplete information to players or multiple players. Actually, this hand, I should add that as a bullet here. This is 2 or more players actually, thinking about maximizing payoff, but they have incomplete information. If you ever imagine your parents buying a house, you submit a bid, a secret closed bid, and you don't know what the other people are bidding either. So you're trying to get the house, you're trying to pay the least amount that's bigger than everybody else based on all the information you have. And so and you're making a move simultaneously. So if you and I were to play rock, paper, scissors, like rock, paper, scissors, shoot, that's economic game theory. I don't know what you're going to do, and we're going to move simultaneously. So then there's 2 over here on the left. So on average, they mean economic game theory. They even give Nobel Prizes for this work. And at Berkeley, they've given quite a few of them. So the other thing is, if you think about board games that you've played, notice that almost all of this is the same. So these are board games, not matrix games. The general form of games you might have ever played, I'll just highlight this, are tic-tac-toe or chess or Connect Four, Othello, many of these games, checkers. These games, so R.C. Bell has this board and table games for many civilizations. People have been playing these games for thousands of years. If you go back to the history of game theory and computational game theory, there's a film called Searching Bobby Fischer, which talks about this amazing chess prodigy. Here you have complete information. Incomplete information means I don't know everything there is about. I don't know what you're holding. I don't know what you're going to do, rock, paper, or scissors. Complete information says that everything that is known about a game is on the table. You can see it. It's known. There's nothing hidden. We're going to alternate moves. There's no simultaneous moves. There's no like, well, if you do this, I'll do that. That's kind of a probabilistic model over here in economic game theory. We don't do that. And the goal can vary. So this is actually the most general case. This is basically saying, let's use computer horsepower to brute force and work a game and then learn from it and deduce what the principles are, or maybe store the whole tree. I store the whole tree. By the way, there's no AI here. This is kind of considered an AI because it's called a British Museum search. It's an exhaustive search of the game space. That's still AI. It's just not what people think of AI, where you have limited information and you kind of do progressive deepening or some A star, alpha, beta pruning of the tree. In this, what I do is I visit the entire tree. I strongly solve the game. Combinatorial game theory is almost the same, but there's a lot of beautiful mathematics behind it. And these games are distinct from the computational, more general case of games. These are really it's like a subcategory of computational game theory because it's all the same goal, but the goal is only the last move. So any of these games in which the goal is the last move, I pull them out and say, this is really combinatorial game theory. And you never have to tell somebody what. So if I'm going to describe a game here, I'd say, well, okay, well, how do you move and how do you win? That's how I would say it's computational game theory. In combinatorial game theory, I don't need to say that. I just say, how do you move? Because we all agree that how do you win is to get the last move. Okay, so we're going to focus on computational game theory. By the way, feel free to ask questions. Maybe you're asking questions for the audience. It's kind of fun. This is a one-way podcast, but feel free to ask questions if I'm going too fast. So you say, well, Dan, if you're talking about computational game theory, what board games do you mean? Well, I mentioned there's no chance. There's like, if you have dice or shuffle cards, I can't play those games. So I don't play, dominoes where you have, the dominoes are hidden. I don't play any card games, any shuffled cards, any dice. Both players have complete information. I mentioned that. Now, there's no hidden information. There's a game called Magic and Stratego in which Stratego, I have my army and you have your army, and Battleship. There's no chance there, but I don't, and it's still alternating play, but I don't know what, the whole point of that game is I don't know where you've hidden your ships. In Stratego, I don't know how you've rearranged your army. Same idea. we don't consider those games. So this means you cannot have any hidden information. So I would not be able to solve and consider Stratego, because really to do that I have to say, well, what if the probability is you have your spy is over here versus over there? Like, it's just that's not what I do. There's already enough games in the in the space that I consider that I don't do that. So there's two players. I actually consider one player games, and those are puzzles, and I have those too, but I'll get to that if we have time at the end. So we call them players left and right. That comes from Berkeley, Camp, Conway, and Guy. They usually alternate moves, but here's the thing: you can have a repeat move. So if it's my turn and for some reason you have no move and you have to skip, this happens in the game of Othello or reverse side where you have no moves, and the game allows that. And now I would make two moves in a row. So that's legal and allowed. That's okay, but you can't have simultaneous moves. It never says, okay, mostly both of you make a move at the same time. That wouldn't work. And unlike combinatorial games, in which you only win by making the last move, these games end in a pattern or capture or the absence of move or something like that. So any general ending is valid as long as there is an ending. You have to have some terminal positions. So I mentioned before, we strongly solve the game, which means we exhaustively search the game tree and visit every single position, every single move. Technically, you don't have to visit every position to solve a game. That's called a weak solve. The folks who solved checkers, there's a Chinook piece of software, Jonathan Schaefer, University of Alberta, solved checkers, and he solved it with a weak solution, which means he proved that it was a draw. You can prove what the answer is. I'm going to get to some of the proof of it here, the language we use for it. But he didn't have to visit every position. It's kind of a clever thing he did. I want to have a system that can play for any two humans. It can watch you kind of like kibitz and watch from the sidelines and tell you who did well and who messed up. And so I need to know for every position and really every move, but I only need to store the positions for every position, what the value is. Okay, so I'm assuming alternate play here. So let's just pretend that Othello isn't in this. It's a little bit a subtle difference to add Othello, but it's not that much harder. So let's consider we're only going to be your turn, my turn, your turn, my turn. We're always going to alternate play. The value, I consider the value for the player whose turn it is. It's a very egocentric model. It says, if it's my move, if it's my turn, this is the value to me, okay? So I divide the game's positions into 4 categories: winning, tying, losing, and drawing. And I'll talk about them in a second. So winning one, so winning means I'm a winning position. So just give you a sense, every position is a circle, every move is an arrow. So every move is an action. You can think the move is a verb, right? It's an action word. And a position is a static photograph of the board. That's a position. And we always take a picture of the board and also label it by whose turn it is. Like in chess puzzles, you can take a picture of the board. If you've ever seen these chess puzzles, here's a picture of a photograph of a board, or representation graphically, and then they say white to move or black to move. So they embed whose turn it is onto the board. That's not what they do in combinatorial game theory, and there's reasons behind that. But in computational game theory, we store whose turn it is with the board. Okay, so if it's my turn and you tell me that I have a winning position, then that must mean I have a winning move. There must exist a winning move. And because we're alternating play always, my winning move yields a losing position for you, if that makes sense. So I'm going to win because you're going to lose. And this arrow exists. There exists a winning move. Said another way, there exists a losing child. These are parents up here, and these are children moves in the graph theory. So I'm a winning position because I have a losing child, okay, which means I can reach it in one move. Now, I might also have tie moves, and that's it's not as good. You know, you can always mess up in a winning position, and well, not always, but often you can mess up, and here's a way to mess up. You can make a tie move, and then this would be a tie child. That means you would tie on your turn. Or I could make a losing move, and the losing move would yield a winning position for you. So it's kind of this opposite where green leads to red leads to green. And this is very dark red. We did this because actual bright blue and bright red are locked into the colors of the pieces. And so we want to color code the arrows of the moves. And so we chose colors that are not that. But you asked me, why did I choose these? And I chose them because they look like a stoplight. So if you think about a reverse stoplight where red is bad, stop, yellow is caution, good. In California, yellow means accelerate, and that's a joke. And green is go. So green's good, winning. Yellow is like medium, and red is bad. So just think about that. When you chose it, I chose these colors when I was visualizing this to think about that. So this is all my invention, this color coding of this. Now, second one is a losing position. So conversely, if you have a losing position, it means almost like being caught to the corner. There's no good moves. So this is a losing position because every move is a losing move. It's like, there's nothing you can do. You're a trapped rat in the corner. There's no way out. And every move yields a winning child or a winning position for your opponent. So there's nothing you can do. So this is like a flip-flop. Played perfectly, watch this. If there's a game that only has winning and losing positions, if I have a winning position and I make a good move, I'm going to give you a losing. And then your position is losing, you're going to give me a winning, and we'll just go back and forth. I'll always have a winning position. In theory, if I play perfectly, I'll always make the winning move. One of the winning moves, might be many of them. And then you'll have no option but to give me back a winning. So it's like this really fun flip-flop in a perfect play. Here's the third kind of value, which is called a tie value. So a tie position, and you see this in tic-tac-toe, is one where there is a tie move. There is no winning move. If there were, then there'd be a winning position. There's no. So there's a tie move, and this tie move yields a tie child. So that means I would tie and you get there. You might have some losing moves. You might have some, remember, there's always a chance to just mess the game up. But you ignore those because those are really bad moves. There's always a chance that I'm playing chess and I just give you my queen. Oh, I guess I gave you my queen. That'd be probably a losing move. And then you'd have a winning position. Now, a draw, there are some games that don't have draw possibilities, that aren't loopy. That might mean there's a loop. Now, not all loopy games have draws, but you might have a draw position out of a loopy game, a game that in which if I made a move, I'd come back to a position I've seen before. And not all of those positions end up being evaluated as draws, but sometimes they are. And you might imagine a game where if you and I, our job is to move a piece forward, and if the piece ever falls off the cliff, the person who jumps off the cliff dies. So I move a piece forward, you move a piece forward, and now the piece is on the edge of the cliff. We're obviously not going to jump it forward. That's a terrible move. So you move it sideways, I move it sideways. We just keep wiggling the piece at the edge of the cliff, if that makes sense. So that's kind of a game where, like chess with two kings, you just wiggle it around and nobody's going to win. And so a draw position is one in which there might be some losing moves. As I said, I might mess up and jump it off the cliff. That would be really dumb of me. But there is a way for me to survive and keep the draw. So I'll move it to the side, and now it's to you, and you just move it back and forth. We just wiggle back and forth here. So not all draw positions have losing moves. If you and I have two kings, somehow, the way the chess ended up, there's two kings, there actually is nothing but draw moves in those. But in many draw positions, you have potentials to lose, and there's some beautiful mathematics behind that. So those are the four categories: winning positions, losing positions, tie positions, and draw positions. In summary, winning positions have a losing child. Boop. I may have a winning and tying child. We talked about that. Tying positions are here. There's no losing child, so that if it were, it'd be winning. But there are tie childs. And if you don't have any losing childs or any tie childs, there's only three categories, then you will have a winning child. And this is ignoring draws for a second. And you have this one. And draws are, this one draw has a draw child. So that means you can't force a win or be forced to lose. We also store something called remoteness, which is how long a game ends in perfect play. So if the winning position tried to win it as fast as they could, and the losing position tried to lose as slow as they could to try to extend the game, to try to give a chance to not die, then you get this definition of remoteness, which is really quite nice. Okay, so let me show an example. And actually, this is the fun one. I'm going to show you a demo really fast. So here's, if you haven't seen tic-tac-toe, let me just bring that up really briefly. So tic-tac-toe is a game in which you have a 3x3 grid. On your turn, you place an X or an O on an empty square. Once a square is filled, you can't put anything on it. Your goal is to get 3 of your pieces in a row. You're going to place O. If I go first, I'll place X, and you'll place O. It doesn't matter which one actually starts. We call this partisan symmetric. Doesn't really matter which one starts. And then your goal is to get 3 in a row of your pieces in any column, any row, or diagonal. So there's 8 possible ways of winning. Okay. And if you can't do it, if you fill the board up, it's a tie. And one of the things that we did in our early version of this is we realized that wouldn't it be cool if I could show you the value of every move. And so what we've done is I've shown a little circle here to indicate what the value of that move is. And so if X goes first, and I call that values visualization, I invented that too. And our group kind of continued to progress and add more software that does that. So if it's X's turn, X goes first, is X goes here, O goes there, X goes here, O goes there, X goes here, O goes there. Now it's X's turn. If X goes here, X wins. X, X, X. So that's great. So X would just win and go right down the middle. That's wonderful. If X goes here, X blocks O from going. O would, in best play, would block X from going. X would go here and nobody would win. So this is a winning move, color coded by the green, like the stoplight. This is a tie move. And finally, I hope you can see my screen just blank for a second. Sometimes I have a thing. And third, this would be a losing move for X, because if X went here, O would say, hey, why did you miss that? Bloop, and O would go here to win. So if X did here, X would lose. So this is value to X. And so this is kind of cool. This is an example of screenshot of our system. This is the old version when we had a Mac implementation of it, a winning move, a tie move, and a losing move. Isn't that kind of cool? Now, misère is tricky. And so let me show you our system now. This is really cool. Let me get to that and change the shared screen window to here. I hope you can see that. And this is our main website. This is gamescrafters.berkeley.edu. It talks about our group, and this is how big our group is. Amazing, right? Huge group of student researchers, some graduate students even. If you click on this top link, play now, you get to this window. And this is Gamesman Uni. This is our amazing interface, and I give all credit to the students who have built this. I built the first version that was a downloadable Tickle TK and C version. They added this web and all these games. It's unbelievable how much work has been put into this. You can choose a game. You can search for a game up here if you can't find the icon for it. And you can click on it. It says tic-tac-toe. And there's tic-tac-toe. And you get two different versions. One is called regular, one's called misère. And we're going to play misère. Now, misère is the opposite. So it's a French word, and it says that whatever the rules for winning the game were, it's the opposite. You still want to win the game, but the rules for winning are the opposite. So, for example, in tic-tac-toe, I mentioned getting 3 in a row would win. You always want to win, but to win, you make the other person get 3 in a row, if that makes sense. So 3 in a row like sets off a bomb, okay? So you don't want to get 3 in a row. So remember that, okay? So here's the game of misère tic-tac-toe. And this is the value. So this already tells you that if you were to go in the corners, you can't win this game. This is a losing move, and then the other person will have a winning move, and if I play against my computer, they'll play perfectly. So let's do this. And let me actually change this to be computer versus, I think this is humans. Let me just go with this now. If I go here, and if you got a chance to hear that, maybe I have a sound here. So let me share. Oh, I don't think I can share with sound.
Or I can hear you.
Oh, you heard me? Okay, great. Yeah, I guess it's by default on. So I moved in the corner, and what it says is if X, who should lose this game if X goes in the outside. Remember, the only way for X to keep a tie was to go in the middle. If you remember that, if I undo this, the only way to do a tie is the middle, which is counterintuitive, because if you don't want to get 3 in a row, this middle is like has 4 different ways through the middle. And so it seems like this is the worst position because it has 4 ways. The edge only has 2, and the corner has 3, if you look at this. So it feels like the edges are the best moves, the corner's next best moves, the middle would be the worst move, but actually the only way to keep a tie is in the middle. It's actually counterintuitive, but really beautiful and elegant. So if I were to move in the corner, how would you respond? As, oh, you're going to go in the edges. Okay, so remember that you go in the edges. Okay, so that's kind of cool. Let me now go back and share the PowerPoint I just had, which I've somehow lost. Oh, there we go. Okay. Bloop. I don't know why I scrolled to the bottom of that. Okay. So here's the fun part. Let me click here. So we actually learned that we could visualize and as a fractal, the perfect move. So here's tic-tac-toe, misère, visualized. Okay. So the game is a tie. Remember, there was a yellow. Because there was a yellow child, if I move that yellow, that was a yellow move, indicating there'd be a yellow child. It was a tie game. So I'm going to label the outside and put a little rim that says it's a tie. And then if I click here, bloop, you remember that the only way to keep the tie was to move in the middle. So what we do is we draw 9 boxes and we color code hollow boxes, and we draw the color code them based on the values from, if you remember, from the game. And now here's the fun part. You can do this recursively. So if you were to move in this upper right square, you then zoom in and make this a 9x9 box. How cool is that? And that, if you remember this, remember the edges. You remember that the edges were the only way to get the win. So if the first player messes up, by going in the top right. The second player, only way that they can win, if the other player tries to play as well as they can, is to grab these winning positions by making the edge moves. Remember that? That was exactly the same as we saw before. And this upper right is blank because this upper right square is already filled in, if that makes sense. The early player moved in the top right, and as a result, this upper right is blank because there is no other move. You can't move on top of another player. So it's kind of cool you see these dots. Now, if I were to do this for every possible move, this is a response. And so this becomes a fractal answer key, if you will, which is if the first player moves on the top, your response is to move on any of these 4 responses. So it's kind of symmetric here. You can see the symmetry going on. So it's really beautiful that my system will generate these as a PDF file, and you can print these. And I actually have one of these in my wallet. I carried around like, hey, look at the answer key for tic-tac-toe. It's really kind of fun. And we can do this for other games. So not only do we create an online system, just to kind of step back a second, not only have we solved the game internally, we then, as I say, we have a server that responds to the values. We have a front end on the web that then lets you play it interactively using JavaScript, talks to the server, gets the values, spits them out. It's a really beautiful system we've architected. And then we also have some C code that can generate the answer key. So this is I can print this for you. I can give you a link to that. If you'd like, I can give your readers a link to the answer key for tic-tac-toe. And we have the answer key for both Misère and regular tic-tac-toe. This is for 2-ply, which means 2 moves. Remember, this is one of the move here, and this is the second move. This is only a 2-ply, kind of like toilet paper. And we have 3-ply in the PDF, and we actually printed a poster that was 4-ply. This gets very big. You imagine this is exponentially growing size. So we have a 4-ply, huge poster of the moves, and it's actually quite beautiful. Okay. So we've done this for other games too. We have solved some of the biggest games that people actually play. When I say solved, not weakly solved, I mean strongly solved. So we have the answer to Connect 4. People play Connect 4 all the time, probably maybe aside from tic-tac-toe, the most popular game in our system that people play. And we're super proud to have one of the only online perfect online perfect players of tic-tac-toe. And we also have, let me just show you this other piece of it, which let me finish this slide and I'll go back to the tic-tac-toe. This is a big deal. It took 960 cores, 5 hours to do. This is some recent master's work from my student, Justin Yakota, who's amazing, brilliant coder and brilliant mathematician. And he decided to take on this and do this as a parallel solve. So 960 cores, which means we did this as a parallel solve. A lot of these games break down into very efficient parallel solving. There's not a lot of shared data. So you can divide the tree up, and each core would only own or know about a certain part of the tree, and then it send it back to some main dispatcher that brings it all together. So this is the answer. This is the answer. Remember, I showed you the recursive picture. This is the recursive picture that our system generated for Connect 4, which is if you have to go to the middle. The only way to win Connect 4, if you play against a perfect opponent, is to make a move in the center. It is a winning game. It's a win for the first player. There's a whole YouTube video that you could link to that. I think it's Numberphile did an analysis of this, and our solve correlates with theirs. So there's kind of a nice backup of 2 independent people solving the game and coming to the same conclusion. It's a win in the middle. If you go to the sides, so it's like, I guess it's 3 and 5, it'd be a tie. And to maintain the tie, you have to go in these children positions. If you make a winning move, then there's only losing moves for the opponent. If you go in the corners or the edges here, I guess 1 and 2 or 6 and 7, that's a losing move. And here are the ways that you can respond to that. So it's kind of interesting to show you that second one. And if you look, there's some small dots, really small dots below that, which is actually how to respond to those losing. If I make this losing move, how do you win? And those small dots are there. So this one, it's really hard to print this one, but we have had some fun thinking about different visualizations for this, but it's really quite beautiful what we come up with. All right, let me show you what this looks like to play with Connect 4. So, I was going to show you before I do that. What we've also come up with something called the visual value history, and this takes a little while to understand. This is the left player. So left is blue, and this is the right player. The left player had a draw move, and it was draw in 9. It's a tie. Sorry, it's a tie game. There's no draw circles here. It's a tie game. So we remember tie is yellow. So tie in 9, and this is like almost like the Squid Game or a tug of war. Your goal is to pull the game to your side, if that makes sense. So the first player, we visualize this as, if I can undo this, I'll just show what it looks like. We visualize it as kind of two equal yellow things that are just going to extend. So if I made perfect play, watch what happens here. Make perfect play. And by the way, this is showing you the values of the moves. So say there is a move here that's a losing move, which will give a win to right. And there is a tie move that will yield this position. So let me make this tie move and watch what happens. See, then you get this. And now it basically is this kind of pretty, almost like a sheared off pyramid. It's a trapezoid, if you will. So here is this. If I just keep following yellow, and there might be some red moves in there. There might be some ways to lose this game. But here's another move to, if I'm just going to follow the perfect play. So perfect play is do this and follow the yellow. And notice that it makes this large kind of sheared off pyramid. That's what it looks like when you have a tie. So if I restart this, let me show you what it does. Now, what happens if I make a losing move? So I'm going to make a losing move. Now, right should win. So right has a green position. This means, look, player 2 or right should win this game in 8 moves. And this says I'm 8 moves away. Now, how this works is if you play perfectly, this is one of those. And by the way, if I undo this, it's kind of weird. There's both the yellow move and a green move. And because they're both moves that yield something in 7, they're kind of overlapping each other. So it's hard to see, but there's also a green move here. So it's a little disconcerting that you can't see the green move. But there is a green move, but it happens to be a tie move there and happens to overlap it. So you can't, what are we going to do? We have 2 things that want to be on the same line. So now I'm pulling it. So I made the perfect move. Now you are going to lose in, I guess that was 8. You're going to lose in 7. Look, it says player 1 will lose in 7 in perfect play. And this says that nothing you can do. These are all the same color, and there's nothing you can do. Every move is equally bad. Okay, so I do this. Now you should win in 6. And again, there's a tie move in here, which is overlapping the winning move. So I can find the winning move. I don't want to block this. That would be bad, by the way, to block this. Because you want X to have as many chances to do that. So I'm just going to find one of these greens. And notice, by the way, if you can see this, there are 3 different losing moves. So now player 1 or X, blue, player 1, should lose in 5 moves. So in perfect play, if I'm trying to stretch this out, I've lost this game. I'm X, I went first, I'm player 1, and I'm going to lose this game. But notice that I have different speeds where I'll lose the game. Now, I can stretch the game out as long as I can, and that's this move. That means you should win in 4. Then if I make a kind of semi-medium bad move, that means you'll win in 2. And if I make this move, it's the worst move, you'll win immediately. You win in 0, which means the game is over. Win in 0 means the game is over and you've won. So notice what we do is we actually color code this. Isn't this cool? We call this delta remoteness, which is we color code the red based on how bright red it is. This is kind of dim red. That's the worst move. If you always go for the brightest color, it's the best move. So this is the best move for X, because I'm gonna try to I'm gonna put 5 X's here. Think about it, it's actually harder going first because you have to put 5 X's. O only gets 4. Contrary to tic-tac-toe, in theory, you get 5 pieces to move, and I only had 4 going second. So you always think about it might be better for the first player. Just in general, if you didn't look at the tree, because you have 5 versus 4 players in regular, and here because you don't want to get 3 in a row, 5 is worse for you. Okay, so kind of cool that I color code these. So if I go here, the game's over immediately, and now it says win, and you've won. The other player's won. There's a little icon of like yay, and there's 1. So this is the 1 in 0. The game is over. So if I undo that, this is the best move, and now that's the longest move. See, and now there's still a way for this for O to throw the game. And so this, we call this whenever. Maybe I should do this. Let me try to do. Can O ever lose this game? Let me do this here. Okay, X goes here. Can O ever see? Look, O can actually lose the game. O is supposed to win by just going here, and then X makes it 3 in a row here. But O can actually lose this game. And notice that it's switched over. So O, we call this a fumble, where O is going to run the ball. This is O side, that player 2, red. O is going to run this ball to their goal line, and just if you play perfectly, you'll be able to slowly pull the team to your goal line, just like a tug of war. But O jumped across and made a fumble. So anytime it's across the center line, it means who should win is changed and flipped because somebody made a terrible move. In chess, it'd be a question mark, because you've given the game up or something. So this was, we called a fumble by O, and then X wins immediately because O just lost. Now, if you only have a tie position and you go to then a losing move, we call that a bumble. So it's a fumble or bumble. They kind of rhyme. It's kind of a nice thing. So this is like, it's not a full fumble, but like you could have had a tie, but you now have a loss. So it's like it goes one over. But if you would have won and now you've lost, that is a full flip. And we call that a fumble. So it's kind of cool. We've added some, some words to the vernacular of game theory. So that's a little demo of this. Like if you wanted to, I could click on games. And by the way, we have puzzles too, which are really delightful. I can get into that, but let me just show you some games. And so if I have to search for it, let me find Connect. We have a search feature, Connect 4. Click on this, and here's the full 6x7 game. And there it is. This is the full working. And now look at this. You can turn this off and play the whole game. What we encourage people to do is go here and turn all of this off. You turn it off backwards. You go turn off, turn off, turn off, and turn off. And when I close this, it's just playing normal. And remember, blue is just, it says blue's turn. So it's left's turn. Left is going to make a move. I don't know what left is. Left goes here. I don't know how to play this game. And now it's red's turn. And just red does. So this is just blue and red making twos. Who knows what's happening? We're playing, okay? It's a little slow because it's like looking up the value, but not using it. So this is actually a little slow as it takes a second to look up the value in our API. But now here's the fun. When the game is all over, you can turn this back on, and then you can look at the visualization. Look at this. Look what's happening. Look. So left, blue should have won. Left fumbled. And then right fumbled. So remember, now we can use what we just talked about. And then left fumbled again. And then right fumbled again. And then it came down to here. Now we're here. So isn't that fascinating? That this will tell you kind of what the history of the game is. So it's super fun to play games against another human. You say, well, Dan, isn't it unfair now that you solved the game? There's no more fun in the game. No, there's a lot of fun in these games playing against another human. What you do is you might use our system for this, where you turn off all the visualizations, you just play it, it'll record the game for you. And then when you're all done, you turn all the visualization back on and you find out where did you fumble. So if the first player should have won and they did win, then it means there's exactly an even number of fumbles or some fraction of bumbles in there, which is, look at this. Let's say the game is over right here, okay? So watch this. This is 1 fumble, 2 fumbles, 3, 4. See, every time you have a fumble, it goes back to the original person's side. So now left is going to be able to pull this all the way to the end if there are no more fumbles. If there are no more fumbles, or if there's a continuing an even number. Every time I fumble, you'd fumble back to me. And here was like 4 fumbles in a row, which is a little silly, but we were just moving the edges, not doing anything. But sometimes kids do that. So it's kind of fun to be able to look back and teach yourself how to play the game perfectly based on this visualization. I hope that's really cool. And that is tic-tac-toe. Let me just, while I'm here, show you puzzles. If we still have time in our call, puzzles are really fun. We try to repurpose the winning, losing, and tying of that. There are 2 kinds of puzzles. One puzzle has loops and one puzzle doesn't have loops. So this is a game of peg solitaire. You might have seen this before. This is a delightful game where the goal, I had a game like this as a kid, and the goal is to jump over. Here's a peg, and you can jump over. To make any move on this game, you jump over. It's like 2 in a row and then a blank spot. So the one on the far side jumps over the middle guy, lands in the spot, and then removes a piece. Okay. So we call green moves or winning moves anyone that can, in a game that isn't loopy, can still get to the final goal. And the goal here is to have 1 piece left. So if I just follow green, it's the perfect move. Here, all green, there's no bad moves. Oh, that's a bad move. If I make this move, there's no way to win to only have 1 piece left. But if I follow these greens, there's a lot of greens. Look at this, a lot of ways to keep winning this game. It's like you almost can't lose this game here. And now you see there are some ways to mess up. And near the end, you'll see a lot of, wow, look at this. Like there's almost no way to mess up. This is an amazing game. Like there's very few red. It's pretty fascinating, right? Oh, here we go. A ton of red. Now you have to make the exact right move to do the right thing, and then exactly the right move. And you watch, if I just follow green, it's kind of fun to have this solved for you. And you can do the same thing where you play the game without the visualization, and then you see what did you mess up here. So if you notice, I do this, and now dun, da, 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 I have exactly 1 piece, and I played perfectly down here. So if I undo 1 or 2, let me undo until you see it. Watch. Let me redo. So if I make this move, now no more pieces. So that was, notice, and so how we visualize this is a green move is a move that moves in puzzles that are loop free, like this one. A green move is one that'll get to the solution, and any red move leads to this like fail state where you can't get out of it. And there might be a lot, I remember I showed you at the beginning, there was an early fail state here. If you remember this, there was an early here. If I follow this, I'm now locked in the fail state. Every move is going to be red because there's just no way to get to that. So I'm kind of like a black hole. I'm locked in this failure state. So that's how we use colors in the same mapping, the same kind of red, green. There's no yellows here. There's only red and green because you either win or lose the puzzle. Now, let me go to another puzzle that's loopy. This is a puzzle. You might have seen the sliding block puzzle. So this is a puzzle where you have, we call this the 15 puzzle here, the 9 puzzle, where the goal is to slide these around to get 1, 2, 3, 4, 5, 6, 7, 8 in that order. So here I'm looking at a 18 move perfect thing. Now watch what happens. Every green move, we repurpose the colors. Every green move is a move toward the solution. Every yellow move keeps the same distance to the solution. And this is undoable. So you can never be stuck in a position you can't undo because I can just slide it back. And every red move moves away from the solution. So we kind of repurpose red, green, and blue in this, red, yellow, and green the same way. Here we go. So I'm going to follow any green and just watch what happens. See, don't do this because if I do this, that just undoes it and I move away from the solution. Notice that, see? So if I just follow greens, and by the way, there's a way for the computer to do this. So if I go here and I say, let a computer do this, it'll just solve it perfectly. So watch what happens. Now, just watching it, isn't that kind of cool? You're just watching it play perfectly and solve the puzzle for you. So this can be a fun kind of screensaver for you, or just if you want to do this. And there's a way to actually change the speed, the computer move. You can reduce the speed down so it moves pretty fast. And do that. So watch. So this is pulling from our database and making the perfect move. But notice that as I'm scrolling, see, every move was perfect. Isn't that kind of cool? So it shows you what the value is. Now, these dots are showing you what the potential is. So I messed up over here, but these are showing you what the potential moves are. So these are all green moves, green positions as little circles, but those have been red because you're going away from that. So just showing you where all the children are of that. Okay, isn't that cool? So here's like the position I could have, and I can write even from here. I can still play. I can move away. Maybe I actually did freeze. Interesting. Once it finishes, you can't move anymore. It's funny. I thought you could still move. Okay, so we're all done. So that's cool. So that's how we do puzzles. So we do puzzles and games, and we call puzzles, we consider puzzles one-person games in that sense. So let me go back to my PowerPoint and finish it out. But it was really fun showing a demo. I hope that was really fun to see so we have a live system. I encourage everybody to play this if they want to. This is all free. So in summary, we built a system called Gamesmin. That's our kind of core software. Gamesmin stands for Game Independent Automatic Move Tree Exhaustive Search, Manipulation, and Navigation. So this is game independent, means we handle any number of games. It's automatic, which means it just does it. It's right, the software that just searches the tree there. Move tree exhaustive search. So that means it'll walk the whole game tree with an exhaustive search. Manipulation means you can modify the game tree by changing the rules. So remember I talked about misère was we modified the rules rather than the rule being 3 in a row wins, 3 in a row loses. That's how you manipulate the rules, which manipulates the game tree, makes a whole new game tree. And navigation means we let you play the system. So it's kind of a cool thing. And we made this acronym up like 35 years ago when we have started the system. This is crazy. It's 1988. I started this project as a fun side project, and it grew into this unbelievable, 250,000 lines of open source software, collaborative project over 20 years. I've been doing this. I started in 2001. So we're actually more than 20 years of doing this. The code base is in C. Then we had a Tcl front end. Then we moved to JavaScript and Python. And we still have C for the fast stuff and Python for some of the smaller games and puzzles. And JavaScript is now our front end for our website. It's exhaustive search of the game tree, input is the starting positions, the move and the win conditions. So what you need to tell my system how to play the game is very little. It's like, okay, here's how the game works. Here's how you make a move. Here's how you win. And here's where you start. That's it. Let it go. And it just does its whole thing. It's pretty magical. And this is an early screenshot of what it looked like. So that's my research. It's one of the 2 research projects. I'll stop screen sharing now. It's one of the 2 research projects that I do. One is in computer science education, research development, but this is really my passion project. I have much more fun, to be frank. I have more fun doing the game theory stuff because that was something that I really, was doing as a kid, and the kid in me comes out when I work with many students, and we have about, 30, sometimes 30 or 40 students working with me every semester. Imagine that. Imagine a research group with 40 students all working on different projects, all letting their interests drive what they do. It's super fun. So it's been a joy running this group. I think it's one of the longest research groups at Berkeley. As I said, we've done this since 2001. I call it a research and development group because we both are pushing the edges of computational game theory, but also we do a lot of software development. Really, there's kind of two pieces of it. And I'll just give you a little taste of some of the projects we're working on now. One of them is a robot project. We have a one-armed robot, a 60-degree of freedom robot that can play perfectly. It calls into our API, knows how to make the move, and can play perfectly. That's a super cool. I have an amazing grad student working on that. Another is I have visualization. So we have a camera, and the camera is going to look at a board. And so imagine you and I would play on a physical board, like Connect 4. And then I have a camera looking over your shoulder at the board and noticing when the move goes in, and then the camera will put the value into our system. I mentioned before that if you go to our system, you can turn off all the colors, and you and I will just play Connect 4, and then we'll see who won at the end of the day. Well, we know who won, but we'll see who messed up and who fumbled and bumbled. Wouldn't it be cool if you could have click a button on a website and say load camera, and so JavaScript somehow gets access to your camera. You place the camera and adjust it somehow, and then you and I would just play a game, and the camera would know when you made a move or I made a move, who messed up, and then whose turn it was, and then it would essentially make the moves like our visualization was. So as you made a move, bloop, you'd see the visualization of it make the move here. So the camera would be kind of driving rather than clicking buttons. The camera would be driving this. People have said, well, Dan, why don't you make an online system where you can log in? And what I found is it's not as that really that isn't such an interesting project, because you and I could play over Zoom, and I could let you control my mouse. So if both of us are controlling mice, then basically we can both make a move on the system. So you can play this. You don't need to build in a whole back end where people would log in and make an account and play it. Let somebody else do that. We basically focused on. It's easy to get too many projects, and then they just die on the vine because none of the students to make them actually real in our system. So I really do care about adding games that are adding features to having projects that have a real impact, and people can finish them and really solidly finish it out. So I'm excited about our robot projects. I'm excited about a lot of our projects. We also have a parallel solver project, which ends up having a group of students who want to work and write solvers for parallel. I mentioned parallel solver for Connect 4. Do that. So it's pretty exciting. It's an exciting space, and it's a wonderful group to be part of. I think we're in our 2024, so we're in our 23rd year of running this. It's just wonderful. 24th year of running this. It's really great. So that's my project, Games Crafters. It's one of the two things that I do, and it's something that I'm really passionate about, and I'm glad to be able to share with you and your audience.
Yeah, thank you. That was a wonderful presentation. So I also wanted to ask you, if someone's an incoming freshman at UC Berkeley, are there any clubs or programs that the university offers that you think are interesting?
Oh, there's a ton. There's something called Tabling Day, where students have a table. If you have a group, like maybe you're doing a weightlifting club and you really want to teach people how to be fit and lift weights and do that, you can have a table about that. So that's an exciting space. There are, I can't tell you how many clubs there are. So they're all student driven. There's a cappella, and there's this. This is a faculty led research project. So this is a project where I'm the one at the top of I'm the one organizing. I'm the one letting people. Students get credit for it. What's really great about this is students can get kind of class credit, or they can get research credit. There's two ways to come into this group, and it depends really whether you're doing more of a development project or a research project. But there's also development as part of research as well. So students can come to my group one of two ways. I've almost had too much success where I have now, as I said, 40 or 50 students, and we're totally packed into the room and it's too much. We have to kind of prune that down maybe this next semester. But there's lots of opportunities. When you get to Berkeley, there's 100 different student clubs you can reach. And the only thing I'll add is don't spread yourself too thin. If you're a freshman, join and kind of limit yourself to how many different things you decide to join, just because it's really easy to get pulled into all these ways and you don't have time for your academics. So make sure you have some time to do that. So that's it. I hope that was useful to your audience.
Yeah, thank you for joining me.
Wonderful. So it was really a pleasure to be able to share this with you and to share my love of game theory, my love of the research of game theory and research development of game theory with you and your audience. It's great. Go STEM.
All right, bye.
Thanks a lot. Take care now. Bye bye.